Okay, let's start with priority queues. See, there is a difference between priority queue and heap. And what are we learning in this session? Both. So what is the difference actually? Priority queue is an ADT, abstract data type, and heap is the best implementation of this priority queue ADT. Okay, so we will learn all this. Okay, so we will start with priority queue ADT. We will see the basic functions this ADT has, and then we will see 4 implementations of this priority queue ADT. So using unsorted list, using sorted list, using array-based heap, using tree-based heap. Okay, so these two are linear data structures. Linear data structures. And these two are non-linear data structures. Non-linear data structures. Okay, 2 are linear data structures, 2 are non-linear data structures. Okay, next we will see one application of priority queue, that is sorting. We can use heaps for sorting, and that is called heap sort. And we will see how heap sort is related to selection sort and insertion sort. Okay, let's start. So what is a priority queue? A priority queue is you can say ADT, right? ADT. So here we have defined it in terms of a data structure, but assume that it is an ADT. Okay, ADT. So heap is a tree-based data structure. Because the focus of this priority queues is heap, hence we defined it like this. But you can say priority queue as an ADT, it has the functions that we will see, insert and delete. And the best implementation of this priority queue is heap, and heap is a tree-based data structure. Okay, so keep that in mind. Fine. So and whenever people say priority queue, they kind of mean heap. Okay, they don't mean it as an ADT. So assume that you know all these differences. Sometimes people automatically assume that priority queue is a heap. So you need to understand that in that case, it is a data structure. So in the other cases where this is generic, it exposes these functions, you can consider priority queue as an ADT. Okay, so what is the style of operations here? So here I have used some phrase. This is not a standard phrase. Okay, whatever in priority out, whatever goes in, right? How does it come out? Priority out. The item that has the highest priority will come out. Okay, so you have seen FIFO, right? First in, first out. And then, so what are the other types of data structures you have seen?
Last in, first out.
Last in, first out, right? And what about this? Whatever in, priority out, right? So whichever has the highest priority will come first. Okay, and so on. And this priority queue has 2 major operations or functions, insert and delete min. So there is something called decrease key also that you will learn in other graduate courses. Okay, not here. We will not cover decrease keys. We will only cover insert, delete min. Okay. Next. So what are some of the applications of priority queues? I mean, think about any application that has priorities. Flight queue that has customer priority. Call center queue, customer priority. Technical support queue, customer priority. Vaccination queue, citizen priority. So on, right? So any application that has priorities, priority number 1, or importance is 2, importance is 3, class A, class B, class C, right?
NER.
Yes, exactly, right? So on any application that has priority, classes, divisions, groups, right? So on. Okay, along with that, we can also use priority queues for sorting. Sorting. So how? So we will see that, okay? So what is a priority here? And think about it, the smallest element has the highest priority. So you can use it for sorting also. If you can use priority queue for sorting, you can use priority queue for any application that requires sorting, right? Okay, next. Oh, so one more point, right? So priority queue, is it a linear data structure or non-linear data structure? As I said, priority queue as in ADT, it depends on the implementation. So if you used a normal unsorted list or sorted list, it is really what? A linear data structure. So if you use a heap, that is a non-linear data structure. Okay. So we'll see. Priority queue ADT. Now let's see the most important functions in this priority queue ADT. The insert function and remove min or delete min function. Insert is k comma v. See, we are inserting pairs, right? You can also insert one key, that is fine, right? Or key value pairs, doesn't matter. So it's very generic, key value pairs or key. Fine, insert of key comma v. What is remove min? Min, the element or the entry or the pair, key comma value pair, that has the highest priority. So here when we say min, we really mean priority is 1. So lower key value, right? A lower key means higher priority. Hence we say remove min. Okay, so we call this as min priority queue. You can also define max priority queue if you want, right? So here we will assume that highest priority means minimum. So you can also define highest priority means maximum and create all these functions. Now very simple. Okay, min, it just returns the min, it does not delete the min. Okay, size and empty are obvious functions. Next, so let's see. What are the operations? Insert, remove min. Yeah, these are the two major operations. Minor operations are min, is empty, size, so on, right? Okay, let's see. Insert of 5 comma a. 5 comma a is in the priority queue. Insert of 9 comma c. See, this is a set. It feels like this is an ordered set. So it is too difficult to represent, how this is implemented, because the implementation depends on whatever you're using. If you're using an unsorted array, it won't be sorted like this, right? It need not be sorted like this. Look at this insert of 3 comma b. So 3 has the highest priority, then 5, then 9. But if you use an unsorted list, it won't be stored like this. But this is more of a conceptual collection, right? In this conceptual collection of these entries, right? Which has the highest priority, which has the second highest priority, third highest priority, so on. Okay, min, you get the min entry 3b, but you're not deleting 3b. Next, remove min, 3b is removed. Then you have 5a and 9c only. Insert 7d, 7d will sit in between 5 and 9. As I said, right, this is more of a conceptual collection and not exactly how it is stored in the data structure. Okay. Next. Let's see 4 different types of implementations for priority queue ADT. So these are the simple functions. Currently, we don't care about this, okay? Just focus on insert and delete min. See, we can use unsorted list, we can use sorted list, array-based heap, linked tree-based heap. Okay, so if it is an unsorted list, what happens? Unsorted list, or you can consider that as an unsorted array, right? Dynamic array, whatever. Okay, insert. Insert is very easy. What do? Insert at the end position, right? Constant time. What about remove min? End time. Why it is end time? You scan the entire array or the unsorted list for the minimum element, and then you delete it, right? Scanning itself can take O of n, and deleting can take O of n, right? So in general, this takes O of n. So that is unsorted list. Okay, what about sorted list? So insert takes n time, remove min takes 1 time. Why did we write it like this? Okay, suppose we are inserting here. So can we insert here in a sorted list?
No, you insert at the very beginning,
Right.
in the
So,
front.
okay, we have to insert it here. Right? Okay, fine. Then you are shifting all the elements, that is O of n. What about remove min? Why is it O of 1? Shouldn't it be?
Will the minimum always be at the top?
Right, the minimum, so inserting can be at arbitrary position, right?
Right,
Can
because
it-
it's sorted.
Yeah.
It can go at any position in that sorted list, right? So in the worst case, it can be O of n, O of n. Why is remove min O of 1? When you delete this,
You can just remember the location.
no. So I mean, when you delete this, shouldn't you shift all the elements?
You don't have to.
You don't have to. I see. Okay. Right. I mean, you can say something like that, but it is kind of inefficient use of the data structure. What if you insert something that is, lesser than this minimum? Then there will be a lot of holes, right? If you don't shift. So how did you get this O of 1?
Well, because isn't it a queue? So you're just popping off the top?
True, you are removing the top element. That is true. But how are you implementing this? Using sorted list.
Or
So then
circular,
you-
right?
Okay, so
Yeah.
you are thinking of a circular list.
Yeah.
Right. Okay, then it works. Okay, right. So that is the idea. So if you're thinking about a sorted, circular, dynamic array, right, then this works. See, another idea is also simple. So currently you're thinking that the min has to go here, right? Why
Right.
don't you
Yeah.
consider that the min has to go here?
Yes, I think that's what Stacy mentioned. You put it on the top, right? Top means maybe the bottom.
Oh, top. Okay. I mean, not to the left
Yeah.
of the array. Okay. You
Yeah,
mean right
maybe.
of the array?
Yeah, you could
Yeah,
make it at
sorry,
the
that's
top,
what I
right?
meant. Yeah.
I see. I see. Yes. Right. This is one fix. So if you assume that the highest priority is here, then it is an easy fix, right? You don't need to use circular array and all that.
That's right.
But yeah, so there are multiple solutions, right? Okay. So now you see the problems, right? Remove min has highest complexity here. Insert has highest complexity here, right? So this is worst, but what is best? Insert has the best complexity here. remove min has the best complexity here. So the obvious question to ask is it possible to come up with a data structure that can exploit the advantages of two different words and not the disadvantages? Right? Seems like you can prove that it is impossible to have a data structure that takes something like this: O of 1 for insert, O of 1 for remove min. Can you tell me why? Anyone? You can show that it is impossible to have a data structure.
These two are contradictory to each other, I think.
Why?
Because once you satisfy the insert, then how can you make the order or make it sorted?
I mean, that's not a proof, right?
No, it's not a proof. Yeah, okay, yeah.
So how do you prove it?
Okay, prove it.
See, you can prove it, right? That it's impossible to come up with a data structure that has insert and remove min as O of 1. Okay, so we will not go into the details. I will just give you a high level idea. You can explore it further, right? So there is a proof to show that any sorting algorithm, right, that is based on comparison cannot do better than n log n. You cannot come up with any comparison based sorting algorithm better than n log n time. Right? This is must. Right? It's
Okay.
impossible to have a comparison based sorting algorithm that takes less time than this. Okay. So now the question is, if there is a data structure that has insert O of 1 and remove min O of 1, then what can you do? You can create a sorting algorithm that can run in O of n time, isn't it?
Yeah.
You keep inserting n elements into the data structure in n times O of 1 time, right? And similarly, keep deleting the minimum element, removing the minimum element. And that also takes n times O of 1. Then your new sorting algorithm will take n time only.
Mhm.
And that is contradictory. That's impossible because there is a lower bound proof, right? You cannot do better than n log n. Using the decision tree based model, right? There is a simple proof to show that you cannot do better than n log n. Hence, it's impossible to come up with a priority queue, right? Or a data structure such that insert and remove min works in one time. Okay, that's the bad news. But there is a good news also. You can do better than O of n, right? So though you cannot combine O of 1 of this, O of 1 of this one, but you can do better than O of n of this and O of n of this. That is the heap data structure, right? I mean, this was the original motivation in coming up with heap. Okay. So though we cannot exploit the advantages of both these implementations, we can also do better than the disadvantages of, both these data structures, and that is heap. So the complexity is log n in both cases. Insert is log n, remove min is log n. So it's way better than n, but it is worse than 1. Correct? So something in the middle ground. So this is kind of a hybrid. So the beauty of this is it is neither unsorted nor sorted. Right? It's not sorted. It's not unsorted. I mean, think about your hash table. What is hash table? It is unsorted. What about your balanced search tree? It is sorted. Okay, hash table is unsorted, has very
Yeah.
good expected complexity. Balanced tree is sorted, right? Your balanced tree is sorted. There, the complexity is all log n, right? What about heap? Heap is neither sorted nor unsorted. It lies somewhere in between. It's partially ordered, partially sorted. I mean, you don't even call it partially sorted. You can say it lives in the word between sorted and unsorted. There is some ordering. There is some ordering. It's too difficult to exploit that ordering, but there is some ordering and there is disordering, right?
Yes,
So the
sir.
combination of that gives you this. Yes.
So you mentioned that the hash table is not sorted, but in my mind, the keys are kind of sorted. You use the key as an index, which is, say, like in our homework, you have 11 hash values. So the hash goes from 0 to 10. So in that sense, not considering the collision, it should be kind of sorted, right? Is it?
So you are considering that the indices in a hash table are sorted.
That's
In
what I
fact,
think, right?
in fact, indices in any array is sorted, but this is not important. What is important is key itself. Key
Okay.
1, key 2. So what do you do here? Key 3. This
Okay.
can go here. This can go here,
That's right. Yes.
right? So
Okay.
this is unsorted,
That's true. Yes. Okay.
right? This itself is unsorted. So this is more important. So we define it on this one. Keys themselves are unsorted, right? It can appear anywhere. And sometimes you can have key 100 that can take the same position of key 2, right? Collisions. So all these things can happen. So this is unsorted. Balanced tree is sorted, but heap is somewhere in between. Okay. See, you can think of this. Assume that unsorted is kind of dead. Sorted means something that is living. Heap is somewhere in between. It's neither living nor dead. Okay. Fine. Now let's look at unsorted list. It is easy. We will probably skip it. I mean, you can think about this, right? We already talked about this, how this works. Okay, so we will not go into the details. So we already talked about unsorted list, sorted list, and we analyze why the complexity is all this. Now let's move to the heap. Heap is the best implementation, best way to implement a priority queue. And heap is a non-linear data structure. Okay. Right. So as we were discussing, you see that the advantages of the, both these structures could not be actually combined, right? So the complexity we have is worse than the advantages, but better than the disadvantages, right? Somewhere in between. Now you can ask a question. What do we achieve using a heap? It's log n. Insert is log n. Remove min is log n. Now you think about balanced search tree. In balanced search tree also insert is log n, delete is log n, search is log n. Of course, worst case, right? Everything is worst case. Then finding min is log n, finding max is log n. So finding min is log n, removing that min is also log n. So every operation seems log n. So balanced search tree not only solves the problem of all these insert and remove min, but it does in log n time. And not just that, it can also handle many other operations. Then why should we care about heap? Anyone? You got the question, right? Balanced search tree is so powerful data structure. You can insert delete, search, find min, find max, find predecessor, find successor, remove min, remove max, remove predecessor, remove successor, everything in login. So beautiful, powerful data structure. Then why should we learn heap? Doesn't balance tree automatically cover all these operations? Anyone? Any ideas?
If you don't need the sorting algorithms, heap is a simpler data structure ADT than balance search tree, right?
Balance search tree. Yes. So it's not that we are doing theoretically better than balance search tree here. This is not asymptotically better than balance search tree in any way, right? And balance search tree, I mean, it also stores every element in the sorted order. In order traversal of all the elements in a tree, balance tree is sorted. Still, we use heap if an application only requires insert and removal. The reason is this is a lightweight data structure. That's the takeaway. Okay, this is a very lightweight data structure. And as we discussed earlier, you can also use a DQ instead of a stack, right? You can use a DQ instead of a stack. You can use DQ instead of a queue because DQ is more powerful. It can solve many more operations. It can solve anything stack can solve. It can solve anything heap can, a queue can solve. But why do we don't go for DQ? Because if we can get away with extra operations, right, we go for stack or queue. Those stacks and queues are lightweight data structures compared to DQ, right? I mean, DQ is, of course, it can solve more problems. That means there will be more operations. There will be more maintenance of all those variables and everything, right? So similarly, balanced search tree is a powerful data structure, no doubt. That's a top level data structure, right?
Professor?
Okay, let me complete the statement.
Oh,
However,
sure.
because heap is so lightweight, right? So try to use heap whenever your application just cares for only these two operations. Yes.
I'm just thinking about what you had said earlier about how we want to always find the simplest solution to a problem. Right. So in this case, if all we ever need is insert and remove min, we would use a heap over a balanced search tree. I guess I'm wondering by doing that, are we setting ourselves up to run into problems in the future? Like say something comes along and we need to change it and now we need to do more to it. Would it be better to use something that has more flexibility?
Right. So that's a trade-off, right? So do you want more flexibility, more modularity, more generality, or more performance?
Okay.
If your aim is more performance, go for, stack, queue, heap, so on. If your aim is generality, so that in the future, if more clients or customers are asked for more operations, maybe you need to implement it. So then go for the most generic data structure.
I see. Okay, thank you.
Right? Okay. Yes, that's a very good question. It's a trade-off between performance and generality, right? So why did we go for classes? Using classes is slower than directly using the functions, right? Because it's more modular, it's more general, it has easy maintainability, and you can have security, object-oriented concept, and so on. A lot of advantages. But what are the disadvantages? C++ is not as fast as C, right? So similarly, there is always this clash between generality and high performance. So you need to, decide based on what are the requisites of your software. Okay. Next. So let's move to examples. Okay. So here is your tree. This is your tree and this is heap. Okay. So you're seeing key value pairs everywhere, and the key is the priority, and the value can be anything. It can be a record, it can be a URL, whatever, file name, anything, any employee database, employee record. So okay, so we care for the minimum value or minimum key. Minimum key means highest priority item, and we are saying that this is a heap. Why do we say that? Okay, what is the definition of a heap? So before we look at the formal definition, right? So let's try to understand this example. So this looks like a binary tree. Okay, this is a binary tree. And what else? Look at this. This is a perfect tree, right? So I forgot those terms, whatever we covered. Perfect means this, right? The last but one level has all the nodes. See, so this has 2 power 0 nodes. This has 2 power 1 nodes, 2 power 2 nodes, fully, this is a complete tree, perfect tree. Okay, what about the last level? In the last level, the nodes are from left to right. So what was the definition of this kind of a tree? Was it called a complete tree? I forgot.
It's complete but not perfect.
Okay, complete but not perfect. I mean, this was perfect, but if you include the last level, right, then it is a complete, right? Good. And again, as I said, there are different terminologies used in different textbooks. Anani Levitin uses a different terminology, and Goodrich uses a different terminology. There is no universal consensus on which term has to be used. Okay, so some people use perfect tree to mean complete tree to mean almost complete tree. I mean, so on. There are so many phrases for the same concept. Okay, so that's one thing, right? That is related to structure. And there is also another property that is related to the relationship. What is that relationship? Look at this. This number 4 is bigger than all elements below. Sorry, smaller than all elements.
Smaller, yeah.
Here. Or you can say the parent node has a smaller key than its child nodes. The parent node has smaller key than its child nodes. 6 is smaller than 7 and 20. 15 is smaller than 16 and 25. Right? Similarly, that is satisfied here, everywhere. So there are 2 properties a heap has to satisfy. What is that? One is the structural property. The structural property is something like this. The shape should be something like this. So the perfect tree till the last but one level, and the nodes in the last level should be from left to right. That is the structural property. Then there is the relational property that defines how the relationship between the elements themselves. Okay, now we are ready to define heap. So heap is a binary tree, and a binary tree is a nonlinear data structure, hence heap is a nonlinear data structure. Okay, so it has to satisfy 2 properties, relational property and structural property. So in that relational property, we call it as the heap order property. key stored at a node is less than or equal to the key stored at its child nodes. And here we said equal, but if you assume that all keys are distinct, there are no duplicates, and we will assume that there are no duplicates, then you can see that keys stored at a node is less than the keys stored at its child nodes. This automatically means key stored at a node is smaller than all keys stored in the descendants of this node. Make sense? So that is the heap order property. Next, you have structural property. Structural property is simple, right? It's the, here we use it as almost complete binary tree. This phrase is used in a Levitin's book. But Goodrich book, I think he uses the term complete binary tree property, right? So complete tree means the last but one level is completely filled, and in the last level, the nodes are from left to right. That's it. Okay, so a heap has to satisfy two properties: relational property and structural property. And relational property is very simple. See here, the key at any node is smaller than all keys in the descendants, right? Or you can say a key at any node is lesser than the keys in its child nodes. That's it, right? Okay, now look at this. You can say that there is some kind of ordering. What is that some kind of ordering? Look at this. From root to leaf, this is sorted. From root to leaf, this path is sorted. 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 Right? Every path from root to leaf is sorted. However, there is no clear relation between the siblings. Here, left sibling is smaller than right sibling. So here, left sibling is greater than right sibling. So this is smaller, this is greater. So we cannot find the order between the siblings. Got it? So you cannot say that this data structure is completely unordered. It's not like an unordered list. There is some ordering. What is that some ordering? Every path from root to leaf is ordered. It's sorted. So there is ordering. But it's not like sorting, right? The in-order traversal of this, there is no meaning to that. That's unsorted, right? By luck, it can be sorted, but in most cases, it is not. The in-order traversal, in most cases, it is not sorted. So you cannot say it is sorted. So can you say it is partially sorted? Maybe, right? We don't strictly define it that way, but there is some sorting, right? Hence, this state of heap that is in between, completely sorted and completely unsorted makes it suitable to have better performance for these operations. Right? Okay. Next, let's look at the two operations, most important operations of heap: insert, delete. And we know why we needed only these two, right? Because in a priority queue, and think about a flight queue or something like that. They say, okay, all class A people, right, or passengers come forward, right? Something like that. So that is based on priority. or you can say all senior citizens will have vaccinations first, right? Or all medical professionals will have vaccinations first. So that is again priority. So what is important there? Insert is the way they come in, right? What a deletement is the way they are served. The way they are served. Right? These are the only two operations there. Is there anything else? There is no searching there, right? So insert and delete, right? So that's why the heap came into the picture. Okay, now let's look at the fundamental logic of how heap is implemented. So we are looking at two operations, insert and delete. Let's start with insert. So how do you insert a key value pair? I mean, you can just insert key, but you can insert key value pair also, right? These are kind of interchangeable. In heap sort, you don't have value, but in general, you can have this value. Okay, so you want to insert key value pair. So what do you do? How do you insert? The logic is simple, right? So what we will do is, this is your heap. This is your heap, right? Insert pair k comma v at the last node. So you are inserting here. This is your last node. Last empty node, right? Last empty node. Insert your a new node here. Insert pair k comma v at the last node here. This is a new node. And then up heap bubble until heap order property is not violated. Up heap bubble until the heap order property is not violated. What do you mean by up heap bubble? We will understand how this works, but up heap bubble just means that, you know, try to go from this node to the root and fix any node that is violating the property. That's it. Insert at the last node and up heap bubble and fix if the property is violated. That's it. And you know that the height of a complete tree is log n, right? It's log n. So the complexity will be log n. Okay.
So
Yes.
Professor, quick question. So here you showed the complete but imperfect tree. So if it's imperfect tree, then we add to the last level, right? The very left. Okay. Thank you.
Correct. Right. So wherever, I mean, from the left to right, what is the next position that you can insert?
Okay.
Okay. Now let's look at an example. I mean, it's very easy to understand the heap, the insert operation, right? Using an example. Okay, let's start. This is our heap. Is this a heap? Can you tell me, is this a heap?
It is.
4 is lesser than 5 and 6. Okay. 5 is lesser than 15 and 9. Fine. 6 is this. Right? The property is satisfied here. The heap order property. Is that correct? And the structural property is satisfied. Correct. So this is a heap. Okay. Now we want to add 2 comma t. So where is the next location where we can add a node? Here, right? So when we go from left to right, this is where we have a node available. I mean, or we can insert. Okay, we add this 2 comma t here. What do we do? Now look at all the other paths, right? There is no other problem. But look at the path from this inserted node to the root. We are only interested in this path. Okay. Now let's see. Is the heap order property violated anywhere? The structural property is satisfied. There is no problem with the structural property, right? The heap order property, is it violated?
Yes.
Where?
Just the last one. The
Okay.
20 and 2, right?
20. 2 and 20. It's violated here. So what we do is we compare. Okay, so team, please mute. So we compare 2 and 20, and we see that 2 should be less than 20. That means 2 should be the parent of 20, right? So what we do? We swap. We swap. If it is out of order, we swap. Simple idea. Compare with the parent. If it is out of order, we swap. Now you see that the heap order property is satisfied at 20, but it is violated at 2 because 2 is less than 6. So 2 should be the parent of 6, isn't it? So when you compare 6 and 2, you see that 2 should go to the 6 location and 6 should go to the 2 location. So we swap. So the heap order property is satisfied at 6. It is satisfied here, it is satisfied here. So what are we doing essentially? The property violation, right? The property is violated and we do a fix by swapping. And when we do a fix, the violation, the property violation will go up by 1 step. And when it goes up, I mean, that property may be violated, may not be violated. But keep doing this until everything is fixed. In the worst case, you will have to traverse the entire path from root to leaf, leaf to root. And this height is really log n, right? You know that in a perfect tree or even a complete tree, the height is log n. The difference is plus or minus 1, right? I mean, it doesn't matter. Asymptotically, the height is log n. So this takes time, log n, and make sure that the heap order property is satisfied and the structural property is satisfied. Okay,
I have a question.
Fine. Let's finish this and then we'll take the question. Okay, now we still compare 2 and 4. They are out of order, right? So what do? Swap. And is the heap order property satisfied? Yes, it is satisfied everywhere. See, whenever we inserted a node here, of course, the heap orders property was satisfied everywhere here because we are not touching it. The only problem that can happen is in that path. The path. Now we are fixing, right, by moving along this line path from leaf to root and swapping, continuously swapping until we hit the root or the property is fixed. Okay. Yes, questions?
Yeah. So on one of the previous slides, it was saying that these heaps they need to have at least 2 I nodes at the level I. So it's not a complete tree, like you said. Like you can have an incomplete layer, but when you're adding a node like you are here, doesn't it make the most sense to add it to the branch that doesn't have like all it that isn't like a completed branch? Like it doesn't have like all the, because each level can have 2 to the I nodes at that level. So wouldn't it make sense to add it like as that branch as you did, as opposed to like adding it and making a new level down at like on the left branch, for example?
Okay, so see, the definition of heap says that until the last but one level, it is perfect. There are no holes. The holes are only here, right? In the last level, right? In the rightmost portion. So are you saying that we need to change the location of the inserted node?
No, I was just asking about because on the previous slide, it basically just said each level can have, each level has 2i nodes, which isn't a full level.
Oh, right.
Which-
So this is 2 power 0 nodes. This is right. This has complete nodes here. Complete nodes, right? All the
Yes,
nodes
complete
here
nodes.
possible. Correct.
And then the last level doesn't have complete nodes.
Correct.
And then, but then it was saying, like 2i, not 2 to the I, it was 2i. And so the way I read that, I thought that was saying that, like, yeah, you can have, like 6 nodes at level 3 and then 8 nodes at level 4. So then you'd have this kind of like missing tree on the right side, but then it wouldn't be a perfect up until the last level. So,
Oh, I see. So, what I said is there are no missing holes or nodes until the last but one level.
I see. Okay. So,
right, there are no missing levels or nodes there, right? Everything is complete. That's the definition of complete tree.
Yep.
The problem or the holes happens only at the last level, right? So that's the definition of the complete tree.
Yep. Okay.
Hence we are inserting at this position. Okay.
Yep, that's good. Thank you.
Yes. Okay, so now we know how insert works. Now let's look at remove min. So how does remove min work? Delete min, remove min, right? Remove the root node. I mean, we will look at the example, just know this, right? Remove the root node, move the last node to the root node position, down heap bubble until heap order property is not violated. Okay, remember this, right? Immediately remove the root node, move the last node to the root node position, down heap bubble. So we will understand, I mean, you understand up heap bubble conceptually, right? You understand the concept. You keep swapping until the property is fixed, right? Similarly, down heap bubble is also the same thing. But up heap bubble goes from leaf to root. Down heap bubble goes from root to leaf. But the concept is very, very, very similar. Okay, now let's take an example. So you want to do delete min. Where is the min?
The root.
The min is always at the root. The highest priority element is always at the root. Okay, now can you tell me where is the second highest priority element?
Somewhere at the next level.
Okay, so it is at the next level, maybe this level?
Well, we don't know which direction is going to be the higher priority.
Either this or this, right?
Yeah.
Okay, now can you tell me where can be the node which has third highest priority?
No, we can't specify that.
No, it is the possibilities, range of
It's just the level 2
The level.
in this.
level 2.
Well,
Are you sure?
Should be
No.
level 2, yes.
well, it could be level 1.
Yeah,
Or
could
level
be
2.
level 1, yes. That's true.
So what is the answer?
The answer is we don't know.
No. I mean, range of possibilities, right? That range of possibilities is fixed. Can it be this node?
Could be.
Really?
Yeah. It depends on how many levels, right? 0, 1, 2, 3. Then yeah, that could be that level.
So this can be a third priority item?
Yes, it's log n, right? It's log n. So here, I mean, if we are talking about level 3, then root is level 0, then 5a is level 1, 9f is level 2, then
Okay,
14e
so
is
this
level
is
3.
impossible.
Why
This
not
is
impossible?
impossible.
Okay.
The reason is, see, if this is highest priority,
Yeah.
and the second highest priority is one of these two nodes, right?
Yeah.
Right? Second highest priority items cannot be below this. So similarly, the
Oh, you mean yes. Yeah.
highest priority items
Yeah.
is one of these three, one of the elements here in this range. It can be here or here.
Yeah.
It can never be here.
Yeah. Okay. Maybe we have a difference about the level. I mean, I thought you talk about the top one as a 0.
No.
Priority.
Level number is correct.
Yeah.
But the third highest priority item, right?
Yeah.
1 is this, 2 is this, 3 is this.
Yes, that's true. The level goes beyond below that level. Yes.
Right.
Yes.
So the third highest priority element cannot be below this at all.
That's true. Yes.
But you don't know. I mean, as Stacy said, it can be at the second level also, or it can be at, second level in the sense, what is this? Yeah, this level, or it can be at this.
Yes.
So we don't know, right? But this is the range of possibilities. This is impossibility.
Mhm.
Okay, know all this. Okay. Now let's look at delete min. So we know that min is at the root. So we want to delete it. Let's delete it. Remove 4c, right? And return it. Okay. I mean, this is the ultimate value you will return, but you will need to fix it now, right? So now this node, root node, is empty. So what should we do? Take the last node value and move that to the root node. Because if the root node is empty, something has to take its position, right? So which will take its position? The last node. Okay, why should the last node take its position? The idea is simple. You need to make sure that the structural property is always satisfied. You don't want to move this node. It doesn't make sense, right? This will be a hole. You don't want to move this node. You don't want to move this node. It's simple if you move this node, right? Okay, so this will be now, empty. This will not be a node. Move the node, the value from there to the root. Now your heap will be something like this. Your data structure is something like this. Can you tell me, is this a heap?
No.
No, you violated the
Right.
what is called the order property.
Okay, now let's look at this. Is the structural property satisfied?
Yes.
Yes. Now we need to deal with the heap order property only, right?
Mhm.
Okay, where is it violated?
The 13 it's bigger, greater than 5 and 6.
13. Okay, so how should we fix it? Now we do a down heap bubble. That means we try to push that violation of heap order property to the leaf from the root until it is fixed. Right? This is down heap bubble. So what do? We look at the child nodes of 13. The child nodes of 13 are 5 and 6. Which is the minimum element of 5 and 6? It is 5. Right? So what we do is we swap 13 and 5. Right? We swap 13 and the smallest element among its child nodes, that is 5. Again check, is the heap order property satisfied at the root? Right? It is satisfied. The heap order property is satisfied here, but what about this? Is it satisfied?
No.
No. Why? Because 13 is greater than 9. Now again, what is the smallest element among these two child nodes of 13? 9. And 9 is smaller than 13. So 9 should move up, right? Swap 13 and 9. Swap 13 and 9. Same idea, right? When you swap, 9 goes up, 13 comes down. So if you analyze the heap order property satisfied here, here. What about 13? No, it's not satisfied. So take the smallest element of its child nodes, 12 and 14, that is 12. 12 is smaller than 13. So swap, right? When you swap, what happens? (12, 13). Now, do you have any other nodes that you can, check a child nodes of 13? No, right? Now you see that the heap order property is satisfied everywhere.
Yes.
The structural property, of course, there is no change. It was satisfied throughout. The heap order property was violated at the root. And what did we do? We did a down heap bubble. So we started from the root, right? So here, and we looked at the smallest element among its child nodes, that is 5. Compare 5 and 13. If 5 is less than 13, swap. Compare 13 and the child nodes. I mean, the smallest element of the child nodes is 9. If 9 is less than 13, so swap. Compare 13 and 12, because 12 is the minimum among 14 and 12. 12 is less than 13, so swap. And you hit the rock bottom, that is the leaf node. There are no other child nodes that you can explore. That's it. You have fixed the heap order property everywhere, from the root till the leaf, everywhere. And you see that the violation of this property goes in a path from root to leaf, right? It does not go everywhere. So the only things you need to check is one path from root to leaf. If you fix it, you're done. This is your removement. And what is the complexity? The height of this tree, the height of this tree is log n, so the complexity is log n. Make sense?
Yes.
Okay, so we understand the core idea, core logic, how insert works and how delete min works in a heap. Now we will look at some implementation details of this. That's it, right? That means we understand the core idea, core logic. Now we will look at two different implementations. Are we looking at two different implementations? Probably not. I think we will focus majorly on array-based representation, and we will not really look at link tree-based representation implementation. Okay. Now let's look at the array-based heap. What do you mean by array-based heap? See, you can store a binary tree as an array. And we have seen this concept before. This is not the first time we are seeing this. Where did we encounter this? In binary trees. You can, if you want, you can store it as a linked tree. If you want, you can store a tree as an array. Just because you stored it as an array does not make it a linear data structure. Right? Array is not always linear. It depends on how you are accessing the elements. You're not accessing the elements one after the other. You're jumping here from parent to child and all, right? Though you're storing it as an array, the way you are accessing is in a non-linear fashion. Hence, even though you use an array, it's not a linear data structure, it's a highly non-linear data structure. Okay, and what's the idea we used when in trees? We said we can use level order, or what is it called? Level order traversing, right? Or level ordering of the tree. And you know how that works, right? We covered all these things in detail. We'll be using that here. That's it. Okay. So the numbers will be, see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the indices of the array 0 to 12. And you store all the keys and values in those locations of the array. And you know, what is the relationship? Look at this 7q. 7q is parent of 11 and 13, right? What is the index? 5 is a parent of 11 and 12. Look at this. 5 is a parent of 11 and 12. 11 is the left child, because 5 into 2 plus 1 is equal to 11. 11 is the left child of 5. 12 is the right child of 5. 5 times 2 plus 2 is equal to 12. Hence, 12 is the right child of 5. So here I mean the indices, right? The values at these indices. Okay, 7q and 11 and 13 are the children of 7q. Okay, you know all this because we covered all these things. So suppose we use this array-based implementation. Okay, now let's look at the code. Heap order or heap priority queue, array list. We will be using an array list. And what is an array list? We covered this also, right? What is an array list? What is an array list? What's the difference between an array and an array list?
Array list can extend in size after it's already been defined.
It does not have a fixed size?
Yes.
Right. So it's a dynamic array and you have all these functions on this array, right? So you implement this as a, you know, ADT, get, set, all these things. Okay, fine. And it's a dynamic array. And we also saw the, what is that? Amortized complexity of array list and all, right? Okay, next you have the constructors, leave this, size min, insert, remove min, then up heap, down, up heap bubble, down heap bubble, heapify, right? Swap operations, parent, left child, right child, has left child, has right child, so on. All these functions. Okay, so we will understand these functions one by one. Insert. Okay, let's try to understand the insert function. See, everywhere you're inserting a key value pair, right? The key value pair is written as an entry here, entry of key value pair. Okay, so check key, unimportant, leave this, and nivest, create this key comma value pair. Okay, so these are the two most important steps. Heap dot add. What is a heap? Heap is the array list. Look at this. Heap is the array list of entries, array list of key comma value pairs. So in insert, you insert the key comma value pair, that entry, into the heap array list. Add automatically adds it to the last node, right? That's the meaning of add. Add means add last in an array list. Okay, and then you do up heap bubble of heap size minus 1. So what is the idea here? So this was your heap. Line 5 represents you added one entry here, and line 6 will call a function to say upheave bubble and fix all the violations of properties. That's the meaning of upheave bubble. And what is this entry? Upheave bubble from this node. This is the index. Heap dot size minus 1 is the index. You give the index of the node, then you will be doing an upheave bubble of the heap from that particular index. If you had given another index here, it will do an upheave bubble from that node. Okay, so given any index, it does the upheave bubble from that particular node. I mean, we only want to do upheave bubble from the last inserted node, right? Newly inserted node. So we are using heap dot size minus 1 because that is the last entry. Okay, fine. Now let's see upheave bubble. So as I already said, right? So what is the meaning of upheave bubble? Let's try to understand that. Upheave bubble. So what do you do here? Upheave from index j, right? Index j. Suppose this is your index j, and suppose this is your parent of j, parent of j. So what do we do here? We check if the key at j is smaller than the key at p. That's what we do, right? If the key at j is smaller than the key at p, what is the meaning of that? That means they are not in a proper order. Right? The heap order property is violated. If it is violated, we swap of the index j and index p. That will swap the elements. Right? Okay. Now let's look at this. When will we will not do a swap? There are two cases when we will not do a swap. And think about it, these are the base cases, right? What is the base case here? When the value, when the key at j is greater than or equal to the key at p, we will not swap. And not just that, we will end upheave bubble. That means it is in sorted order, right? If it is in sorted order, you're certain that from here, everything else is in sorted order. Hence you break. Right? Hence you break. That's one. So another idea when you break is when j, when you hit the root. When you hit the root. So that's why you have while j greater than 0. You don't want to go at that root, right? Because there is no parent of the root. Hence, you always say j greater than 0. This is one condition when the process stops. Another condition when the process stops is when they are in the correct order. If it is in the correct order, you don't need to look at its parent and so on. You can completely break. Break means kind of return. That's it, done. Makes sense, right? And we already understand this logic. So see if j is less than, the key at j is less than the key at p, swap. Then swap here if they are out of order. Swap here if they are out of order. Keep doing it until you hit the root or the order is satisfied. Like when you keep doing that, you need to consider this also. J will be the parent, right? Once you do a swap, J is your parent. Okay, so that's it, right? So anything else You want to understand here? That's the major logic of upheave bubble. Okay. Next, removement. So what is removement? So there are three major lines here, right? Remove the root. The root has index 0. That's your answer, and return that answer. That's your removement, right? It's the root node. Get of 0 is getting the root node, because the min will always be in the array. The minimum element will always be here. Okay, and you're returning that. That's your answer. Fine. Then you swap the root node and the last node. Swap the root node and the last node. And then you remove the last node, because that is redundant, right? That is already removed. Hence, I mean, the value has been removed. So you want to delete that node also. Remove that node. This is simple. Then you do a down heap bubble from the root, 0. The index is 0. But which path? See, in upheave bubble, given a leaf, you exactly know the path. But in the down heap bubble, given the root, you have no idea about the path. Only when you traverse, you will get to know the path. How? Because you need to compare the two child nodes, whichever is lower, right? That path will be chosen. So you have to only scan to know the path. Okay. So down heap of 0. Let's see. Down heap. So though there are so many lines, the idea is actually simple. Okay. So down heap at G. So what is the meaning of down heap at G? Okay, so we are starting from down heap of 0, right, from the root, but you define the function for arbitrary node. So down heap from a node J. What is the meaning of this? So the idea is this: you consider both the child nodes, right? Both the child nodes of J. Now you take the minimum of these child nodes, left child node and right child node. What is the minimum of left child node and right child node? So that's what is given here. Left index is equal to left of J. Right index is equal to right of J. You get the child nodes. And then you compare the keys of these two child nodes. And you consider the one that has the smallest key. So that is the logic here. Small child index. Initially, you assign it as left index, and via a comparison, right, you can check whether the right child has a smaller index. At the end, you will have the index of the smallest key among these child nodes in small child index. Okay, suppose this is your small child index. Then what do? You compare that node and the J node. Check whether the key is greater than the key of J. If it is smaller than the key at J, what do? You swap. You swap. So this is the, let me write it as small child index, right? So this was left child of J. This is the right child of J. You compare and store the index of the one that has the smallest key in small child index. You compare that key with J if it is out of order in the sense, so the value here, the key here is smaller than the key here, then you do a swap. and update the value of j. Now the j will be this. Keep doing it. I mean, this is the core logic. Keep doing it. This is the recursive case. Now, what is the base case? When does the process stop? When does the process stop? See, I mean, if you had used a link tree representation, right, you can think about this recursive formulation. This is a recursive idea, right? We are using array, hence we are trying to write it as a, in a non-recursive fashion. But if you have a link tree representation, you can use a recursive formulation. Anyway, so when will this process stop? That's your base case. The process stops when you hit the dead end. When is that dead end? There are two dead ends here. See, one is there is no left child of j. What is the meaning of has no left child of j? That means you have gone to the rock bottom here, right? You are at the leaf, has left child of j. So that is the dead end. That is one base case. What is the other base case? The other base case is when the heap order property is satisfied, right? If the heap order property is satisfied, you are done. So there are two base cases, like in your up heap, right? There are two base cases here. Okay, makes sense? So that's the idea. Okay, so we are down with down heap. And parent, all these are simple, right? Parent is j minus 1 by 2, left is 2j plus 1, right is 2j plus 2, and has left. What is has left? Find the left child and check whether it is in the range of the heap. The range, right? The range of the heap is from 0 to heap dot size minus 1. These are the indices. Check whether the left child is in this range of indices. Similarly, has right is in the range of indices. So these are simple. Complexity is log n, right? This is easy to see. So I will skip this. Okay, now let's go to priority queue sort. The priority queue sort, is kind of simple. So what's the idea here? As we already discussed, insert n elements into the heap. Okay, I shouldn't say heap. Let me say priority queue, because based on this implementation, the complexity will change, right? Insert the n elements into the priority queue. Remove the n elements one by one from the priority queue. That's your priority queue sort. This is not one sorting algorithm. This is a scheme. Why do we call it as a scheme? Because depending on the implementation of this priority queue, you get different algorithms. Okay, so I don't need to show you this one, right? This is easier. Now, suppose you use an unsorted list to implement this priority queue. Then what happens? Look at this. You are inserting these elements one by one. This is an unsorted list, right? So you insert 7, then you insert 4, then you insert 8, so on. So how much time does this take? There are n operations and they take 1 time. What about delete min? You scan everything and get 2 as the output, and scan everything and remove it, right? And scan everything and get the minimum, that is 3. Scan everything and take the minimum, that is 4. Scan everything in the remaining set and take the minimum, that is 5, and so on. So each of this, so this takes what time? In time. worst case n time. This takes n minus 1 time, n minus 2 time, so on. So the total complexity of this itself is O of n squared. So inserting is n, repeatedly applying delete min will give you O of n squared. So the total complexity will be O of n squared. And what is this? This is your selection sort algorithm, right? Selection sort algorithm. Make sense? Okay, if you implement P as a sorted list, what do you get? Now this is simple. Insert 7. Okay, 7 is inserted. Then insert 4. This is a sorted list. In a sorted list, what happens? Each insert is costly. It takes a lot of time, right? So you can assume this is 1, then this is 2, in the worst case 2, in the worst case 3, in the worst case 4, so on up till in the worst case n. So the overall complexity is O of n squared. And once you have this, delete min, right? This is a sorted list. Removing, I mean, assume that it is in the reverse order or circular list, whatever. So this is so easy. Then the total time taken is O of 1 times n. So insert is costly here. So the total time complexity is O of n squared. And what is this? This is your insertion sort algorithm. Correct? See, just by changing the implementation of this priority queue, you are getting different algorithms. Now let's look at heap sort. Heap sort, what is the idea here? Keep inserting the elements one by one. This takes, say, 1 time. So this takes, say, log 2 time, right? Log 3 time, log 4 time, so on up till log n time. So what is the total complexity? N log n. And delete min, right? Log n, log n minus 1, log n minus 2, so on. What is the total time complexity for delete min? N log n, right? The stage 1 of inserts takes the same time as stage 2 of removements or delete mins. That is n log n. See, compare this. Phase time was more here. Phase 1 time was more. Phase 2 time was more here. If you try to distribute in a nice way, you get equal time for phase 1 and phase 2. Right? Log n, I mean, you can assume that the time taken is log n everywhere, right? So n log n for inserts, n log n for removements. So overall complexity n log n. So this is your heap sort algorithm. And this is also one of the fastest sorting algorithms out there. Okay, so try to implement this sorting algorithm from scratch, right? Not just using a heap. So try to implement this from scratch. Okay, so that's about priority queues. Though one can do all n inserts in n time, we are not going to look at that concept. Okay, so we are done. So let me stop recording.